Hello everyone, and welcome to a really fascinating episode of BioLogic Science News. Today I want to talk about a recent study that came out of NASA that documents how blood and clotting action and plasma volume and stuff like that is affected by time spent in zero gravity. NASA has known for a long time that the body undergoes significant alterations when exposed to zero G. For instance, the eyeballs become more perfectly spherical when released from the grip of gravity, and this interferes with the eye's ability to focus images. The lack of gravity also puts a lot less ambient stress on the bones and the muscles, and in time they each begin to degrade. Muscle tissue withers and atrophies because of the lack of weight to stimulate the tissue, and bone density drops at an accelerating rate for the same reason. Furthermore, our vasculature is designed to pump body fluids against the forces of gravity. We even have specialized valves in our leg veins that prevents backflow for this very reason. But in space, there is no gravity pulling fluid down to our feet, so the body's fluids will disperse equally. The head thus gets much more fluid and blood flow than it would normally receive, while the legs get relatively less blood than they're used to when you're in a gravity well. Previous NASA studies on their astronauts have found that the mass of red blood cells decreases during shorter 10 to 14 day missions, something on the order of a 1% loss of mass per day, which corresponds to around a 10% decrease in blood volume during the short duration missions. This phenomenon is called spaceflight anemia, and until this study, it had only been documented at the end of a short mission. There haven't been nearly as many studies of long-term missions, largely due to the logistical difficulty in preserving blood samples until the mission is over, and of getting samples back to Earth while the mission is still ongoing. Neither option is simple, neither option is entirely practical, and as a result, the effects during long-term missions are much less understood, simply because they're a lot harder to study. And that's where the importance of this new study comes in. The importance is that it documented red blood cell mass and platelet counts and plasma volume for a long-term spaceflight, with measurements taken before takeoff, during the mission while the astronaut is out in space, and after landing back on Earth. Samples were packaged into the usual crate of items that gets regularly sent down from the space station, and they were collected and brought back to the lab within 48 hours of sample creation. What the NASA researchers found was that during longer space missions, when the body was exposed for much longer periods of time to zero gravity, it would find a new stable point for homeostasis. It seems that by entering zero G and becoming exposed to a radically different ambient environment, the body experienced a temporary hiccup in its homeostasis. Plasma volume and red blood cell mass and platelet count dropped. But after enough time in zero G, the body is able to stabilize with a higher concentration of red blood cells and blood platelets and the like. This hiccup in homeostasis occurs again when the astronauts end their mission and re-enter the Earth's atmosphere, going from a zero G environment to one with the full force of 1G, which to the returning astronaut can be a little difficult getting used to. This is also why tests conducted on blood and platelets and plasma taken immediately after re-entry show the characteristically low values. The NASA study concludes that these results are fascinating enough to warrant further investigation, and that any follow-up studies should take effort to analyze plasma volume during long space missions, as this would provide valuable data that would put red blood cell mass, platelet count, blood volume, etc. into a more well-defined and well-understood context.